Hello everyone, today I will be presenting on operational amplifiers, commonly known as op-amps. These components are fundamental in modern electronics and are used in various applications, from signal conditioning to analog computation. The presentation will be cover the following topics: introduction to op-amps, historical evolution, why do we need op-amps, ideal versus real op-amps, function of op-amps, fundamental operational amplifier circuits, an example, and conclusion. Well, what are op-amps? Op-amps are electronic devices with two input terminal, the non-inverting one and inverting one, and one output terminal. The primary function of an op-amp is to amplify the voltage difference between its input terminal. The amplification factor is known as the gain. Op-amps are essential in signal conditioning, analog computation, sensor interfaces, active filters, and voltage regulation. We usually use op-amps in our daily life. For example, detection or amplification of weight, or detection or amplification of sound and light reflection. Well, the next part is historical evolution. In 1941, the first conceptual op-amp was developed at Bell Labs. In 1952, the Philbrick K2W became the first commercial tube op-amp. In 1963, the mu-A 702 was introduced as the first IC op-amp. In 1968, the mu-A 741 became the industry standard, and recent advancements include CMOS op-amps and fully differential designs. Well, why do we need op-amps? Op-amps are crucial for converting analog signals to digital signals for processing in computers and smartphones, and amplifying low power signals from sensors to ensure accurate data representation, and facilitating various electronic functions such as filtering and signal conditioning. In the next part, we are going to talk about ideal and real op-amps. Let's talk about ideal op-amps first. The ideal op-amps has infinite open loop gain, and this resistor is infinite, and the current here is 0, which makes the voltage of two inputs equal, and has infinite input impedance and 0 output impedance. But real op-amps have limitations such as infinite gain and non-zero output impedance, which affect performance. The next part is functions of op-amps. Op-amps perform several key functions. A circuit with an op-amp can amplify a small input signal into a large one and outputs it, or remove unnecessary signals from the input signal and outputs only the necessary signals, or can compare two voltages, or enhance the amount of power like buffer. In the next section, we will see 9 fundamental op-amp circuits that can greatly assist you in circuit analysis. Can view their diagrams, applications, voltage gains, and the equations used to drive these gains. Let's look at an example where we calculate the output voltage of a specific op-amp circuit. First, using the superposition theorem, calculate the positive input voltage, which equals 0.068 volt. Therefore, the negative input is also 0.068 volt. Next, since the sum of input current at a node is 0, the Kirchhoff's current law, write the equation for the negative input and drives the output voltage as 5.768 volt. Finally, we double check by plugging the output voltage, the 5.768 volt, back into the equation to recalculate the negative input voltage. As expected, it remains 0.068 volt, confirming that our output voltage calculation is correct, and it's 5.768 volt. In calculation, op-amps are essential components in electronic systems, enabling the processing of analog signals effectively. Understanding their operation allows an engineer to innovate and optimize electronic designs. And here you can see the references. Thank you for your attention. I'm happy to answer any question you may have.